Please note this webinar presentation reflects the views and findings of the authors and not necessarily those of the United States Environmental Protection Agency.
Welcome and joining us for another in our science webinar series. And this time we're going to be talking about the technical details of the EPA guidance for residential air cleaners. This is the second in a series of air cleaning discussions that are being done by Terry Brennan and Lew Harriman, who are two experts, long-term experts in the field of indoor air quality. They were also consultants on our update that we have recently done and reissued to our air cleaning guidance. The previous webinar was on our consumer guide, and this one is going to go a little bit more in depth to our understanding of current air cleaning alternatives and filtration alternatives, and will be focused on our technical summary. I'll now turn it over to our contractor, who will give you some information about questions after the presentations, and then the next voices you will hear after our contractor, Christina, will be Terry and Lew. Thank you again for coming.
Welcome, everyone. For questions today, please submit your questions using the question function on the panel on your right hand of your screen. We will be taking your questions for discussion at the end of the presentation, so please feel free to put those in throughout our meeting today. Thank you.
Okay, so this is Lew Harriman, and I'll begin our webinar here this afternoon. As Lorraine has outlined, this is the second part of essentially a two-part discussion about the revised EPA guidance for air cleaners in the home. So the air cleaner guidance was updated after a number of years in July of 2018, and that guidance consists of two documents. One is the consumer guide, which was the subject of our webinar last month, and today's discussion will be talking about the technical summary, which is a little bit more detailed discussion about air cleaners in the home. So we are talking here not about commercial buildings. We're talking primarily about residential buildings, and that will be the focus of our discussion. But a little bit of introduction about your two speakers today, and Terry and I like to call ourselves the facilitators because we're both very eager to hear your questions. The information that we put together for you here in connection with EPA is a nice summary, but what's probably more important to you is the questions that you have, and we're quite eager to hear your questions. Just for simplicity's sake, in terms of the interaction, we would like to have those questions come at the end. But if you go ahead, as Christina mentioned, and type them into your interface there, then she can organize them and help us answer those in a nice, organized way towards the end of the webinar. Beginning is myself, but I'll also introduce Terry. Terry is a longtime expert in building science and in indoor air quality, having been a contractor for the Environmental Protection Agency for several decades. Terry is very experienced in all aspects of indoor air quality and also all aspects of building science, and has worked throughout the world and also throughout the nation on complicated problems, including disaster recovery. He was a member of the consulting support team for the most recent, the 2018 update of the EPA's guidance for air cleaners in the home, as was I. My name is Lew Harriman, and I am primarily a guy who deals with humidity and moisture problems in buildings, and through that, the related indoor air quality problems and the energy issues associated with that. And like Terry, I was also a member of the consulting support team for EPA. What we'd like to do first is to just do a 3-item recap of our webinar from last month. And what I'd like to do is also remind you that these webinars are being recorded, as are the questions and answers, and those will be posted on the EPA website. So if you missed last month's first webinar about the 12-page consumer guide, within a few weeks you'll be able to download that or listen to it directly from the EPA website. 3 important takeaways that we thought you would be well informed to know about that webinar. The first is that when we think about air cleaners in the home and all of the different possible pollutants that can be present in the home environment, the first and arguably the most important is PM 2.5. And for those of you who weren't at our webinar the last time, PM 2.5 is the mass of particles, the PM, the particle mass that consists of particles that are 2.5 microns, 2.5 millionths of a meter or smaller. So it's a diameter thing, and how much mass do you have in particles of that dimension, PM 2.5. So that's a shorthand, and we'll be using that in today's webinar as well, PM 2.5. It's arguably the best documented health concern because it is fundamentally the basis of our outdoor air standards as well. So that's pretty well understood as a major health concern. And that's why the focus of the guidance and also our webinar is on that one of the many pollutants in the home. Second is what one might want to do about it if one is a consumer and don't have an awful lot of mind space for this issue of air cleaning. And if you have a central system, a central heating or central air conditioning system, you would be well advised, according to the EPA guidance, to use a filter in that system. And the filter, if it had a rating of 13, MERV 13 or higher, that would be a rather good choice. And today we're going to explain a little bit about why that's true. But just what we're talking about when you say MERV 13, MERV is an acronym, like many acronyms, a little difficult to decode. But MERV means minimum efficiency reporting value. And that is a consensus standard developed by ASHRAE, the Heating and Air Conditioning Engineering Society. And what it means is that that filter has a relatively high efficiency, especially a defined efficiency for small particles. And that's the basic reason why that's the recommendation, is that you can rely on the idea that grade of a filter, if it's 13 or higher, is going to take out a defined number of the small particles that we care most about. And then the third and last point from our earlier webinar is that if you don't have a central system, or if one has a central system but you're threatened by point sources or intermittent sources, such as a wildfire or some other outdoor air event that results in a lot of particulate pollution outdoors, you might want to use a portable air cleaner. And if you do, it would be wise to choose one that had a high CADR. And a high CADR stands for a high clean air delivery rate, high CADR. The higher the better. The more cubic feet per minute of clean air that you have, the higher the clean air delivery rate, the more effective that filter will be in removing particles from the air. So that's a quick summary of last month's 1-hour webinar, and now we'll start with a brief summary of what we're going to talk about today. This is the technical summary, the 72-page document, as opposed to the consumer document, which is only 12. And so with this, we're going to be talking about the fact that we just have one whale of a lot more detail available to us in the EPA technical summary than we do in the consumer guide. It explains in more detail and probably does a better job of explaining why the recommendations are what they are, rather than just what the recommendations are. Number two, an important point is that there are health benefits that accrue from taking small particles out of the air. That's a given. That again is the basis of clean air legislation. That's why we clean or reduce the particulate in the outdoor air, is that the fewer particles there are out there, the better off we are. And so that's also true with filtration. The question is documenting that, and we now have quite a bit of documentation about health benefits from filtration, not just the idea of filtration, but intervention studies that talk about what was or was not achieved. Those benefits are modest. They're not major in most cases, but they are improvements. One of the other points is that the best documentation we have for improvements with air filtration comes not from central systems, but rather from portables. And we'll explain a little bit about why that's true. But the bottom line is that filtration does have health benefits, but the benefits are not, they're not going to necessarily save your life if you have other threats. It's not going to take care of all your health problems, but it will make an improvement. And then finally, the last point is that even though we have a wide variety of consumer choices, which is certainly always a good thing, not all the consumer choices that are available are equally well defined as far as their effectiveness and their safety. And so that is something that is of emerging concern, which is that many of the filtration devices we have are effective, and we know they are, and they've been tested and certified to be so. Many of the other consumer choices, especially those that use high voltage plasma and ionization technologies, while they may or may not be effective, there is no program that certifies them to be safe and effective. So that's something that's worth keeping in mind. So those are the three main takeaways. What we'd like to do now is talk a little bit about the contents, about the overall view. And then after the overall view, I'm going to pass the conversation to Terry, who will give you some of the specifics about PM 2.5. But first, a little bit of discussion here about the table of contents. If you were to get this document, this PDF, which is easily downloadable from the EPA Indoor Air website, you'll see that it's a fairly extensive document. It begins with this summary. It begins with a 5-page summary, which is a very neat partner to the 12-page consumer document, because this provides, again, a very executive overview, especially if you are a manager or someone in charge of, let's say, housing, either low-income housing or housing support. If you wanted to understand a little bit more about the why for the consumer guidance, if you just read those first 5 pages, you'd be much better informed than just reading the consumer document itself in this technical summary. The next point that is reinforced here in the technical summary are the 3 strategies to reduce indoor air pollutants, and one of the most important being to exhaust from cooking as well as bathroom, but especially cooking. And Terry will talk about that a little bit later on as to why that's true. So of the 3 strategies, avoiding particulate buildup inside is a really good idea, and that can be most easily achieved by using a kitchen exhaust hood. And then another discussion in the technical summary that speaks in more detail than it does in the consumer document is this, which is that there's a difference between air cleaner efficiency compared to air cleaner effectiveness. Efficiency is a metric that talks about how many particles are coming out of the airstream. And effectiveness talks about the removal from the space. The difference is this, is that if air is not moving through the device, then it might be an extremely efficient device, but it will not be effective because it's not taking particles out of the space. So those are 2 very different metrics, and it's important to understand that just because one has a terrifically efficient filter does not mean that you will have effective particle removal. To have effective particle removal, you need both an efficient device and one which is operating, which seems obvious on the face of it, but that's the important difference between those 2 terms is efficiency versus effectiveness. Then the next section is quite extensive, and it talks about how different types of air cleaner technologies work. There's about 18 pages on this subject, so probably as much detail as most people would want to have. other than those who are dedicating a big portion of their profession to it. This will give you a nice, clean overview in understandable terms about how these technologies work and what they do and what their advantages are and some of their limitations. We're not going to talk about that in this webinar. We're going to talk in more broad terms about other aspects of air cleaning, rather than the exact methodology by which different technologies take pollutants out of the air. The next section here talks about practical things. So, beyond the simple guidance, if you want more detail about practical guidance for using a portable air cleaner, what you might want to look for on consumer packaging, why you might want to look for that, and what some of the limitations are about existing portables, so that it's not just a magic box. It's understood to be, like any device, a device with useful aspects and some aspects that are not as useful as others. So the practical aspects of portable air cleaners. And then the same type of advice for central systems. Central systems have terrific advantages in that we'll go into that in some detail shortly, but there are practical considerations that you might want to think about as you're thinking about adding to or changing the filtration in one central system. And another item of concern for everyone, of course, is the cost of operation. And with an air cleaner, you have a cost of replacing the air filter on a periodic basis, which varies tremendously according to the device. But in addition to that, you've got to get air through the device. And so now we're talking about electricity to move air through the filter, and that does have a cost. It's not a large cost, but it is a cost. And most people that are interested in technical details immediately would like to know what that costs are. And in this section, you'll see some approximations based on field measurements of power consumed by both central systems and portable systems. Then we will talk about health effects of filtration. We are going to give you a brief synopsis of taking some examples of the health studies that have been published in peer-reviewed literature over the last 15 years, and even some that have been published after the guidance came out, talking about the health effects of filtration. And Terry will give us some discussion in that area. And then I'll wind up, when we get to the wind up here, by talking about research needs and 4 points that would be exceptionally helpful if we could learn them as soon as possible about air cleaning that we would like to know in the community of building science professionals that we don't know now, and we'd love to know. That would be helpful for the public to know. And finally, at the end of the document, of course, as you'd expect, there are the references, several pages of references that form the basis for the recommendations in the guidance itself. So that's an overview of what we've got, what the EPA has managed to put in this wonderful technical summary. And with that, now I'll turn it over to Terry. And Terry, if you can tell us a little bit here in more specific detail about pollutants and what we know about them and PM 2.5.
Thanks, Lew. Good afternoon, folks, and thanks for joining us today. The question that we're starting out with is, well, why are we concerned about this, and how does this compare to other pollutants in the indoor environments? So the graph that you see on the screen now is a summary of work done at Lawrence Berkeley Labs by Jennifer Loeb, and she looked at the universe of indoor contaminants for which we knew that the contaminants were in buildings at measured levels and for which there was health-related data, and then conducted a relative risk analysis. And the way this works for us, excuse me, on the y-axis is the disability-adjusted life years, or DALYs, which is one dolly is equal to the number of years of life lost due to premature death, plus the number of years lost due to illness that results in disabilities. So it sort of combines both the people dying prematurely and people being unable to live their lives as fully functioning adults into one metric so that you can compare across a number of different contaminants. And the important part for me looking at this is that PM 2.5, the particles have the highest number of dailies. And if you look at that Y scale again, you'll see that it goes up in orders of magnitude, factors of 10. It's not linear. So it's the particles in the air having a much larger impact on our health as a nation than the second contaminant that popped up in this scale, which is secondhand smoking. So that's the one reason we're concerned about it, is that the risk factor is very high for exposure to particles in the air. So Lew, let's can you go on to the next slide. The second piece of this is that particle levels indoors are often higher and sometimes much higher than they are in the outdoor air. The health studies are all based on measurements, health effects that are seen and correlated to measurements of particles in outdoor air. And in this graph, we have listed on the x-axis 38 studies where they measure both indoor and outdoor particle levels. And the y-axis is the indoor particle concentration divided by the outdoor particle concentration. So when the indoor-outdoor ratio is greater than 1, that means that it's a greater concentration of particles indoors and outdoors. And you can see that in this case that for something like 3/4 of the studies, the indoor concentrations of particles were greater than the outdoor concentrations, and the ones that had the highest results for the indoors are much higher than the difference between indoors and outdoors for the studies where they found that indoors was lower than outdoors. Go on to the next slide. So we have higher concentrations indoors and outdoors, and a contaminant that is resulting in more injury than other candidate of indoor contaminants. This is just mortality, premature deaths from 2005, work done by FAN, showing the map in the U.S. where the density of the deaths being reported, premature deaths that are related to exposure to particles. And as you can see, they're not distributed uniformly. They're in the places where people live and the places where there's high outdoor air particle counts. Let's go to the next one, Lew. This is a study that was conducted by Brent Stevens and his colleague Zini, and it's a modeling study. They've developed a method of partitioning the exposure to particles. So where does the exposure occur, and to what kinds of particles? Particles of indoor origin, particles of outdoor origin, were exposed. and they're estimating the annual deaths per year for the whole U.S., for the entire U.S. And if you look at the bars on the right-hand side, there are two scenarios, and the first three bars are from one scenario where they calculated the estimated annual deaths from exposure based on a uniform ambient particle concentration. And the scenario on the number two is a different technique for calculating the same estimate of the mortality for each year. But it's done on a regional basis. So the variables for which we had regional data were used to drive that model as opposed to the annual average ambient levels for the three bars on the left. Now, the thing I'd like to point out is that the exposure to particles of outdoor origin outdoors is that little gray bar at the very top of each bar. And all the rest of the boxes that they have down there are exposure to particles in indoor spaces, either homes or workplaces or schools or vehicles or other indoor spaces. And so the by far and away the biggest exposure that's causing this mortality is occurring indoors. And the estimates for the indoor residential buildings are the light blue boxes that are near the top. So that's the exposures that we're getting. It's two things about this, two different methods that arrived at pretty similar results. And the indoor exposures for the residences are a very large fraction, probably like 35 to 45% of the total exposure. So indoors at home is an important place, and it's a place where we can make a difference. So in what ways can we make a difference? This is from a modeling study conducted, again, by Brent Stevens and Stevens and Azimi. And what they did is they estimated they made a model to estimate the indoor exposures for 3 different houses. An existing house that's pretty air leaky and doesn't have any fan-powered ventilation in it. And that's this purple line that says 20 air changes per hour at 50 Pascal pressure difference, like the results from a blower-door test. And as you go to the right, along the x-axis, they're calculating how much the exposure would be reduced by going from a MERV 5 to a HEPA filter in increased efficiency increments. And you can see that, well, you make a pretty big difference as you improve the efficiency. And on the y-axis, the infiltration factor, this is not actually the infiltration rate of outdoor air. This is the infiltration of particles from outdoor air to indoors. So the infiltration factor is, you can think of it as the ratio of the particles in outdoor air divided by the particles in indoor air. Do I have that right? And minus the particles that are deposited. So it's compared to outdoor air, what fraction of the particles in outdoor air do we find in the indoor air persistently. If that makes some sense to folks. So what it means is that in this case, at 38% of the PM of the particulate matter indoors that started out in the outdoor air is about 38% of what's outdoors. So that's probably the best way to think about this. By having a house that's twice as tight, 10 air changes per hour, 50 pascals, only about 20% of it is actually managing to get from outside, transport into the inside, and remain in the indoor air in a persistent way. And if you're sealed up to 3 air changes per hour, that's pretty tight, and it's actually close to, for a lot of the U.S., the international code target for air tightness in houses is in the 3 to 5 air changes per hour, 50 pascals range. And now only about 2% of what's outdoors is found indoors. And so that's a huge reduction in the indoor exposure to particles of outdoor origin by having a more air-sealed building. That brings us to what about particles that are not produced outdoors, not of outdoor origin? What impact can we have on those? Where do they come from, and what can we do about it? And it turns out that many of the particles, airborne particles in the indoor air that originate indoors, originate because we're heating things off or burning things. And so cooking becomes an important source for 2 reasons. One is that it's hard, it produces a lot of particles, and it is located in a place where we can put an exhaust near it. So it's a stationary source. It's not a mobile source. It's not the kids walking around or the dogs. It's something that we can deal with in an engineering way. And here you can see a graph showing from Lance Wallace's work, showing that if you make shrimp scampi, you're going to make a big increase in the particles level in the house. And if you reheat it, you might make an even higher spike in the concentration of particles in indoor air. And for comparison to other known sources of particles in indoor air, you put in a little laser jet printer. And you can see that Lance operating his laser jet printer produced just a tiny little bump compared to what cooking up the shrimp does. Well, there are other sources of indoor particles, and here's a list with emission rates, measured emission rates from the literature. And many of them on this list are at the top end of the list have to do with cooking. Or there are some other things like drying clothes, but it's mostly candles, popping corn, toasting, cooking. Spraying house cleaners is another one that's near the top. But cooking is a major set of activities, and it's something that we can actually have an impact on. When it comes to intervening in exposures inside our homes, we have two major techniques. And one is, if it's stationary source, strong source like the cooking range, you can put an exhaust fan as near to the source as possible, and you can capture those particles before they get the chance to mix in with the rest of the house air. For the other particles that are not from that point source, we can circulate air through the house and filter the particles out of the air that we're circulating using a fan-powered system. And we have in most of our houses a central air handler that may heat and or air condition. And as long as we're already doing that to keep the house in the comfortable temperature range, we can filter that air and collect the particles from the air and have an impact on the concentrations in the house. We also have available to us portable air cleaners that can do that are their own little fan with filter that can be moved around the building. This slide is showing one of our problems with kitchen range exhaust is that you actually have to design them in order for them to really be efficient at capturing particles. And you can see if you look at the red and blue dots up at the top part, where the capture efficiency on the y-axis is 50% and greater. Those all happened when they were doing the experiment by cooking on the back burner. And if you move that to the front burner and you start cooking at the front burner, you can see they're all 50% or below in capture efficiency. So it's really much more effective to be cooking on the back burner. But it's something that a lot of us don't really want to do, is to cook just on the back burner as opposed to the front burner, which is closer and seems more convenient. But capture efficiency is frequently not as good there. You would have to extend the range hood out and improve capture efficiency in order to be cooking on the front burner. Filtration alternative, Lew, and at this point, I will turn it over to you.
Okay. All right, great. Okay. So if we can't get rid of the particles simply by exhausting them, as one can do with the kitchen exhaust, assuming that the kitchen exhaust is being efficient in its capture, and that also assumes that the kitchen exhaust is being used, that it's turned on. So if it is, then we move to the idea of taking particles out of the air with filters, and we have two alternatives. As Terry's outlined, one in a central system, or perhaps a portable, or perhaps more than one portable in a space. So let's talk about those a little bit with respect to the revised EPA guidance. The guidance strongly recommends MERV 13. So again, MERV 13 stands for Minimum Efficiency Reporting Value of a level of 13 or above. And to help visualize what we're talking about, what the guidance is talking about when we're talking about MERV 13. What we've done is to take a picture of three typical filters for furnaces or for central air conditioning systems. The one on the left with the green polyester media in it, they're all the same size, all 16 inches by 25 inches by 1 inch. That has no pleats at all, so it's just a flat surface of non-woven polyester. These sometimes in ancient days used to be made out of rubberized horsehair, and now they're typically made out of polyester. But they're designed principally for protecting equipment, making sure that the cooling or the heating equipment doesn't get clogged and gummed up with filters. These type of filters are available. They're very inexpensive. They don't have any MERV rating because they take very little in the way of larger or smaller particles out. They're for feathers, very large things. The next level, which you can see there, is a white pleated filter with some fairly open, broad pleats, but that still means that there's more surface area available to that the air can pass through, and the more surface area you have of the filtration media, the easier it's going to be to take out a larger number of particles, especially the small ones. So what this photo suggests is that that's maybe a MERV 4 or a MERV 6. In other words, it's going to take, the larger particles out, some percentage of them, and that's certainly going to be improvement over a non-MERV rated filter. The filter on the right is a deeply pleated, many small, they're all the same depth. They're all 1-inch pleats, but one whale of a lot more of them than what you saw in the MERV 4. MERV 6, again, it's more media, it's more filtration paper, fiberglass reinforced paper, many deep pleats, and that has enough surface area so that it's going to take out a defined level, some percentage of the small particles that we care most about, and that's the basis of that recommendation. So, why MERV 13 in more depth? So, this is the result of a Monte Carlo simulation of roughly 1 million different scenarios, varying everything from the infiltration rate into a house to the efficiency of the air distribution system in the house, to the coverage of the air distribution system in the house, to the air leakage into and out of the duct system of the house, of the central system, roughly 1 million different simulations for each of types of filters, a MERV 13 filter versus a MERV 8. And the results that you're seeing there are expressed in terms of modeled removal effectiveness, that is to say, removal from the space, the amount of particles probably removed from the space on the vertical axis. And on the horizontal axis, you see the air handler fan runtime. So in each of those two bands, the MERV 13 band and the MERV 8 band, the center line is the average. So that's for a house of average air tightness. The upper limit is the probable effectiveness from a house which is probably better installed, more perfectly installed, and is more airtight. And then the lower boundary represents the modeled effectiveness in a leaky house, one where you don't have that primary air barrier to prevent the outdoor air particles getting in. How much could a MERV 13 or MERV 8 filter do? So if we look at now what we know from ASHRAE research, and also the work of Marianne Touchy and Jeff Siegel up at University of Toronto that preceded this model, what they did is looked at a wide variety of data from thermostat manufacturers. These days with central thermostats, the two major thermostat manufacturers that have smart thermostats can tell you what percentage of the time the system is running. Is what percentage of the time the system is running. And what we know, or what they have found out from querying those thermostat runtimes, is that typically the runtime is less than 20% of the year. So if a year has 8,760 hours, less than 20% of that time is when the air handler in a central system is likely to be running, and that includes both heating and cooling. There just are not one whale of a lot of hours of air filtration. So if you had a MERV 8 filter, and if you were to take the average of that, you might have particle removal effectiveness from the spaces that it's trying to keep clean of maybe, something less than 20%, maybe 15, 16, 17% effectiveness. So the other 80% of the particle is just going to stay there in the air, even though you've got a nice filter. If the system isn't running long enough to do any good. Whereas even if you have that same amount of runtime and you have a MERV 13 filter, you have maybe anywhere from 2.5 to 3 times the probable effectiveness. So many more of those small particles are likely to be removed from the space, even if you have a relatively short number of hours in the year that the central system is running. So that's one of the principal reasons that the EPA elected to strongly recommend MERV 13 rather than a MERV rating of lower than MERV 13. That's the key thing. Keep in your mind short run times on air conditioning systems and heating systems. Just as a side note to those of our listeners who are involved in HVAC engineering and design, especially for residences, part of this reason that there have short run times is that we tend in our HVAC community to oversize things. And when we oversize things, the system runs a short amount of time to satisfy the thermostat and then turns off. That means that all filtration ceases. So if you size things maybe less than the peak load, then you'll have lots more hours of runtime, which will be of significant benefit for filtration as well as also humidity control. Another thing that from another part of the Indoor Environments Division, the Indoor Air Plus program, this is a program which helps builders certify that they go beyond the minimum standards to create a very nice indoor environment with respect to indoor air. The Indoor Air Plus program notes that installation matters every bit as much, in some cases more, than the actual equipment that's installed. So if it isn't installed and if it isn't measured to be working the way everyone intends it to work, the manufacturer and the installer, if it isn't measured, then it may not be delivering benefits. That's part of the Indoor Air Plus program, is that the airflows have to be measured. The other thing noted in the EPA Air Plus program is that MERV 13, of course, is recommended, and here's something on the installation side, and perhaps an opportunity for manufacturers to consider this too, is that you need an airtight filter rack. So those filters that I showed you pictures of just a couple slides ago, if they slide in and if they're too small for the rack, or if they're too big for the rack, if they're too big, then you got to kind of crush them to get them in there. As you crush them, then the filter doesn't fit snugly in, and air can bypass, can leak around the filter, either above or below or beside the filter. And then basically you don't have the same efficiency of a filter. You got a much lower efficiency filter. So it's important to have a gasketed airtight filter rack so that the air actually goes through the filter in a central system rather than leaking around the side. As we move on to take a few minutes to talk about portables before I turn this back to Terry for a discussion about health consequences and health interventions. If we look at portables, there's a metric that was developed by the Association of Home Appliance Manufacturers, AHAM, Association of Home Appliance Manufacturers, and they number of years ago came up with this system to not only test but also to rate and certify, verify, more accurately verify the performance of portable air cleaners. It's the AHAM Verified program, and the label on consumer packaging is as you see it here on the right-hand side of your screen. And what this program does is it measures and verifies the CADR, the clean air delivery rate of the consumer device, and then that is generally contained on the package. So if you look at the label here, there are a couple things that I'd like you to be conscious of. One is the tobacco smoke. If you look down here on the bottom left of that label, it has tobacco smoke, and there's a number below that of 298. What that means is that of the particles that have a diameter between 9/10 of a micron and 1 micron, so they're really small guys, this device, this tested device, will take out a very large proportion of those, to the point where you could say, of the air that this device delivers, 298 cubic feet per minute, 298 CFM, 298 cubic feet per minute, have been cleaned essentially of tobacco smoke. Now, because if you look over here on the right, there's a larger number under pollen. What that means is that the device is producing perhaps 350 cubic feet per minute, and of those 350 cubic feet per minute, 343 have been cleaned of pollen, because pollen is bigger, chunkier stuff, so it's easier to take out. But of that airflow, probably only 298 could be considered clean of tobacco smoke, of the small particles that we care most about. The other thing that you see on that label is the number of square feet. So I've circled this. It says 450 square feet. And what that number comes from is the idea that you would like to clean the air in a space of a significant number of particles. And I'm going to take you through the AHAM test program and its metrics in short order here. But what this says to the consumer is, if you have a space that's 450 square feet or so, then you can rely on this particular device to clean a very large percentage of the tobacco smoke and an even larger percentage of the pollen from that space. You can rely on it doing that, provided that one follows the assumptions. So then the thing to keep in mind here is that larger numbers are better. So again, if you have a device that is designed to take a significant number of particles out of a room with 450 square feet, if you had a room with 250 square feet instead of 450, this guy here, this air cleaner would make it even cleaner than it would in a larger room. So larger numbers are always better with respect to the clean air delivery rate. Down there, the tobacco, smoke, and pollen numbers, always bigger numbers are better, and larger numbers of square feet are always better in terms of deciding to invest in an air cleaner one way or the other. So then inquiring minds want to know, since we're talking on the technical side a little bit, what are these assumptions behind this label here? So let's talk about the method that AHAM, the Association of Home Appliance Manufacturers, uses to measure the performance. A number of years ago, and this is the current edition, which is about to be updated. This is a 2015 edition of AHAM standard AC1215. So AC1, air cleaner number 1, last updated in 2015. So how is this test performed? Okay. Basically, you have a chamber. It's a sealed chamber. And in this chamber, you have an air cleaning device, and you also have particle generation devices. You have a smoking machine. You have a machine that puts a defined amount of dust in the air and the particle range. And then you have a machine that also produces particles that are larger in the pollen size range. So you got a chamber. You've got the devices which generate an initial concentration of particles, and then you got the air cleaner. First thing you do is you generate the particles in here with the air cleaner off. So nothing's running other than you've got particles in there. And then you measure the concentration decline in the chamber. And that concentration decline in each of those particle ranges basically is a result of things settling out, just kind of falling to the ground or being attracted to the walls or the ceiling of the device, or of the chamber rather. So you get a baseline based on the settling rate. And then the next thing that you do is you regenerate the concentration and then run the air cleaning device. And then the rated removal rate of the device is the difference between the settling rate and the rate achieved in the chamber when the device is actually operating. So you take a baseline and then you measure the improvement above the base settling, normal settling. The other point here is that the calculations are run for room size based on what? Based on 80% removal of the particles in the smallest size range, the smoke size range, after 1 hour of operation. So I'm going to run this for an hour, and after an hour of operation, not 5 minutes, but after an hour of operation, 80% of the particles in the smallest size range are likely to be gone, assuming that the ceiling height is 8 feet. So if you have, this is a test chamber test, of course, and they assume that it's 8 feet because that's what they're measuring, or they're measuring something else. In any case, they're normalizing it to 8-foot ceiling height, a certain number of cubic feet, cubic volume of the space. If you had a room in an older building, let's say a 19th century building with really tall ceilings, or one with a very modern building, maybe an apartment building with 10-foot ceilings, as you might have in a center city of San Francisco or Denver or Boston or Miami. Typically, those ceilings are 10 feet tall. So then you're not going to get 80% removal from that because you have more cubic area. So if you have a higher ceiling than 8 feet, you might want to invest in a filter that has, in a portable filter that has a larger clean air delivery rate because you got more cubic feet to clean. The other assumption inherent in these calculations is that there's no more air exchange with other spaces than 1 air change per hour over the hour in question. So there's always going to be some air leakage in any building to and from a space. The assumption here is that You got particles inside, you got particles outside. You're going to have a little bit of air exchange, but no more than one air change per hour over the course of the hour that the device is operating. So those are two important assumptions, and they can affect your selection or the wisdom of your selection. If you have more than 8-foot ceilings, you probably want a bigger one. If you have an especially leaky building, you probably want to have a larger air filter, one that's designed for more square feet. That would be the case, for instance, if you have very leaky windows, older windows in an older building, or if you crack the windows from time to time and you're living next to a highway, then you probably want a much bigger air cleaner. And one can't expect to clean the air if the windows are open all the time. Okay, so with that in mind, I'll turn it back over to Terry to talk about a little bit of what the EPA has found out about the effectiveness with respect to health effects of interventions due to by putting air cleaners in the home. So Terry, back to you.
Thanks, Lew. This is the part of the talk that I think of as, so why should we do anything about this? And the answer is because in the last 15 or 16 years, since the Institute of Medicine's report on asthma, dozens of new studies have been done, and they actually made interventions. They introduced improved filtration into homes, and they measured a number of things. They, among which are the particle levels in buildings. And of the 20 studies that we review in the technical document, the 19 of the studies, indoor particulate matter concentrations were reduced. So they work. In the interventions that where portable HEPA filters were introduced, and that's far and away the largest number of the studies were studies in which portable air cleaners were introduced into the homes. On average, they were something like about a 50% reduction. So the reductions can be significant. So the people use them, the particle levels are reduced. And the second part of the evidence about, well, why should we do something about this now, it is even more compelling for me because they, in many of the studies, they look at either something like peak expiratory volume and flow, and they look at biomarkers for irritancy and C-reactive proteins, which indicate biomarkers of irritation. So we have either direct health endpoints that were measured or health endpoints that were observed, like a number of visits to the emergency room with asthmatics, or biomarkers measured that where, or at least in 18 of the studies, at least one of these observations or measurements improved as a result of introducing the improved filtration into the home. And what I'd like to do is this first start, we're just going to go through some of the tables for the asthma-related studies. And this is a study where there was fresh air supplied to bedrooms, but no filtration. And there were actually improvements in allergy and asthma symptoms in the homes. And in other of the asthma studies, HEPA filter, portable HEPA filter in the bedroom made some small but significant improvements in the combined asthma outcomes. And in the third study, the affordable HEPA filter in the living room, although it reduced the particulate level in the air, it had no effect on any of the self-reported or measured indicators. So it was mixed results for the asthma. In a fourth study, the HEPA in the bedroom with including outdoor air being added to it, HEPA filter, had reduced the impact of asthma. And in the final study, the HEPA and carbon filtration in the bedroom reduced symptoms. Go ahead. It improved peak expiratory flow by 100%. So let's go to the next one. These next set of tables really have to do with cardiovascular effects and inflammation effects. And for these, again, bear in mind that this is 18 out of 20 studies are showing improvement in these results. The HEPA in the bedroom and living room and 8%, the improvement in microvascular function. HEPA filter in bedroom and living room in an area where there's rural wood smoke, 9% reduction in coronary event predictor and inflammation marker. There we go. And in the next study, the electric filter in the central air system, so that's the air conditioner or the heating system. 60 students in Taiwan, 20% reduction in PM 2.5 to 23 milligrams per, would that be milligrams or micrograms?
Micrograms. Sorry about that, Terry.
Micrograms. That's what I thought, per cubic meter. 11% reduction in blood pressure and 7% reduction in heart rate. And another study with cardiovascular and inflammation results. Portable HEPAs in the bedroom and living room, improvement in the microvascular function. And another study with 83 healthy adults in Vancouver, 40% reduction in PM 2.5. And a reduction in C-reactive protein. C-reactive protein is a sign of inflammation.
So the benefits are there. They are often modest, but they are almost always in the positive direction. So in addition to measured results that show that filters can reduce PM 2.5. There are positive results both on the asthma side and on the cardiovascular and inflammation side from doing that. So not just particles aren't great and you can reduce their concentration. That does work with filters, but you can go beyond that and say that when you do that, there are measurable health benefits or measurements, improvements in health markers more accurately. So now that's great, but the EPA nor everybody else, there are lots of things we'd like to know in the building science community, and so of course would EPA like to know them. And the technical summary outlines several things that would be very useful to know, and the sooner the better. The first one is that these consumer devices that use PCO, plasma, UGVI, basically plasma systems are things that use high voltages to break apart molecules. UGVI, that's ultraviolet energy to passivate or change the bacterial composition, PCO that converts, that helps convert some long volatile organics to shorter volatile organics. Well, we'd like to know more about the effectiveness of those devices. How well do they accomplish the tasks that they advertise as accomplishing? So we'd like to know about how to measure that effectiveness. And then beyond that, from the consumer perspective, it would be very helpful if test standards for removal of VOCs and ultrafine particles being those of half a micron and smaller, like to know if you have a device and it is effective, can it be tested independently and validated as having a repeatable effectiveness in the real world? Just in the same way that AHAM has standards for clean air delivery, it'd be nice to have clean air delivery, air cleaned of the contaminants that these technologies are intending to either passivate or remove from the airstream. Beyond that, another thing that's coming out very broadly in the consumer markets these days is air cleaning, or rather air pollution sensors for volatile organics and also for particles. And these are coming out literally dozens by the day, different vendors with sensors, and it would be really nice to have accurate ones. What we know about this from research is that the sensors that are available today at the consumer cost level, $50, $100, $200, not the $5,000 or $10 or $20 or $50,000 of research. The consumer price sensors are not terribly accurate. One thing that we know from research and measured results is that they're pretty good for predicting, not predicting, but alerting to events. So if you have an event where, let's say, you spill some cleaning fluid or something, those sensors are almost certainly going to pick that up and alert you to the fact that there's something in the air you don't want to be breathing. Same thing with particles, and that's good. But it would also be nice to have repeatable measurements, and we don't have that right now with consumer-grade particle sensors or volatile organic sensors. So that's a bit of a challenge that we'd like to see addressed. And then finally, one of the increasingly popular methods of heating and cooling buildings is by the use of what is called a ductless mini-split, an air conditioning system or a heat pump system that has a condenser outside, one unit outside and a unit inside, and the unit might be hung on a wall. So it doesn't actually have ducts. It just discharges its cooling or heating into the open space. And then there are ducted mini-splits as well, which do connect to very short, very, very small duct systems, same idea. But in both cases, those don't have filters that are very effective from the perspective of small particles. There may be one or two exceptions that aren't completely obvious in the marketplace, but the research that was done for the guidance strongly suggests that they really just don't have anything like a MERV 13 filter available in that class of equipment. So it would be nice to know what the filtration effectiveness is of those systems because they're so widely applied. And if they don't have MERV 13 or in that range, it would be nice if they could be engineered so that they did have that amount of particle filtration, so that when you have that rather than a central system, traditional central system, you're getting some better defined level of filtration of the fine particles that we care most about. So that finishes our brief discussion about the technical summary. Again, the three takeaways that we'd like you to have are that you have quite a bit more technical detail available to you in the technical summary in that 72-page PDF, that the health interventions that were known about when the consulting team helped EPA put this together is that there are modest, but there are significant. They're modest, but not huge improvements. And typically with portables rather than central systems, there's exactly two studies that we saw with the central systems, and whereas there are many, many more, two orders of magnitude more than that, the studies where we could see that portables made a difference. So that would be nice to have more central systems. And then finally, it would be useful to have better definition of not only the effectiveness, but also the safety of the multi-technology air cleaners that have combined an air filter for particles with other technologies, plasma discharge, ionization, chemisorption, all sorts of other technologies available in these things. It's a question as to whether those things are either effective or safe, and it would be good to know that they are both. So that would be good to know in the future with respect to research and also industry programs. So with that, why don't we begin? Terry and I are now eager to hear your questions. So maybe if Christina has some questions that she's been keeping track of, she could fire off a question or two, and Terry and I could take a crack at it and see if we can help you address what you'd like to hear about more specifically. Christina, have you got something for us?
A listener asked if an air cleaner can have any effect on the radon level in a home.
I'm going to pass that one to Terry, because Terry was deeply involved in radon from the get-go. So take it away, Terry. I'm totally ignorant on that one.
Thanks, Lew. It would probably have no impact on the radon concentration, but it would have an impact on the short-lived decay products, the polonium business and lead. Anytime you move air around in a building, the polonium bismuth and lead tend to stick to surfaces. So we know from the research you wouldn't make an impact on the actual radon, but you would lower some of the exposure to alpha particles.
Pretty good question, since radon is one of the things that we know that we don't want to have in houses. Yeah. Another question for us?
Sure. So we've had quite a number of questions on CADR, so we're going to try to summarize this for you. Can you please explain how the CADR numbers or CADR label should be read from a consumer perspective? Is there a scale? In terms of interpreting the numbers under tobacco smoke, dust, and pollen, for example, these do not actually say cubic feet. Why is this not defined under the label?
Well, that's a good question, and I think you'd probably have to ask our friends at the Association of Home Appliance Manufacturers as to why they decided to design the layout of that label the way they did. But there's always a tricky balance. You can appreciate that the CADR measurement technology and certification is a pretty complicated process by the little quick summary that I provided earlier. But one thing that you can always remember is if you're looking at 2 filters or 5 filters, you're looking at a bunch of things at a big box retail store, take a look and look at the numbers. And what you can be sure of is that the bigger that number, both in square feet and in CADR, clean air delivery rate, the bigger the number, the better it is. And that's for 2 reasons. One is that the more clean air you have, the more effective it's going to be at taking air out of any space, no matter how big the space is. More clean air is better. You're right, it doesn't say cubic feet per minute, but that is what it means on that label is cubic feet per minute, and larger amounts of clean air are better. And here's the second thing, which is another thing that certainly from our perspective on the consulting side, we'd like to know is that we'd really like to know what the noise level of these guys is, and that's not on the label. Interestingly, the noise level is part of the CADR test standard, the AAM test standard. You're taking noise measurements when you are doing that. And what consumers probably need to know is that CADR is taken at the highest fan speed, almost always. So in other words, the CADR is achieved at the noisiest possible level of that air cleaner. And you would probably like to know what that noise level is, but they're not going to tell you. So it would be very nice if we had the noise level at which the CADR was achieved, and that would be helpful. So 2 things. For sure, bigger numbers are always better, both in square feet and in and smoke clean air, and keep in mind that it's big. It's better to have a big one, and then you can run it at a lower speed and get the same removal effectiveness that you'd like to have. So oversize those guys. Don't undersize them with respect to the square feet. Are there other questions connected with CADR that we should talk about, Christina?
I think that covers it,
Okay.
Lew. Well, why don't we hop
Great.
on to the next question?
Great.
We received quite a few questions about air changes per hour and tight homes. The first question is, if your house is sealed to 3 air changes per hour and the indoor environment produces the majority of the particles, energy aside, why do I want a tight home? This is assuming the whole house ventilation is the minimum required, including exhaust only. Why not use infiltration as a source of dilution and diversity in the home?
I think that probably Terry's discussion covered that question pretty clearly, which is that if you just are going to use infiltration to ventilate the home, you can be guaranteed that a very large proportion of those particles outside are now going to be inside the home. So instead of just having indoor sources like cooking, you're going to be dragging the outdoor air pollution in as well. To some extent, measurements also show that the building enclosure can provide a certain amount of filtration effect and also a certain amount of buffering of temperature and humidity. That said, do you really want to have air from your basement and from the center of your walls in your breathing zone? And typically the answer is you absolutely don't. So there are many reasons to have a tight building. One is to be sure that you're not dragging in particles from outside. Number one. Number two, you don't want to have drafts come into the house. So if you have a lot of drafts coming in, especially in the summer and the winter extreme seasons, then you're going to be running the system more than you would otherwise because you're trying to achieve comfort when you have nasty air coming in from outside. So overall, tight buildings are a good thing with respect to indoor air quality, provided that you have a source of clean ventilation air, clean and dry ventilation air. So they all go hand in hand. Not a simple discussion, but there's the answer is tight buildings are better, especially when they are ventilated with fresh and clean air.
A follow-up question to that is that tight houses have 3 air changes per hour. Why is the ANSI testing based upon 1 air change per hour?
Okay, so the ANSI, actually, those are 2 different things. Totally different things. Terry, do you want to explain the differences between the test pressure air exchange rate and the air exchange rate under natural circumstances?
Yeah, sure, Lew. The air changes per hour that we talked about for the 3 levels of air tightness in Brent Stevenson's study were 20 air changes per hour and an indoor-outdoor pressure difference of 50 pascals, and 10 air changes per hour, indoor-outdoor air pressure difference of 50 pascals, and 3 air changes per hour at a pressure difference of 50 pascals across the building envelope. So those conditions don't reflect normal air pressure differences that buildings experience or low-rise buildings experience. Anyway, more typically, it's in the 2 to 10 pascal range is what most buildings experience under normal temperature differences and wind speeds and typical wind speeds. So that's a blower door test type air tightness measurement, and the air exchange rate would be much lower than that on average over the course of the year for the houses. So the ANSI, I'm not sure about the ANSI number of 1 air change per hour.
Well, yeah. So again, you'd have to ask the Association of Home Appliance Manufacturers why they selected an assumption of 1 air change per hour with respect to the spaces around the test chamber or the space in question. So you'd have to ask them that, and I'm not quite clear on that. But I'm sure they had to pick some number because there's going to be some air exchange. If you have a room, let's say you have a bedroom, a child's bedroom, which is a very good place to put a portable air filter, especially a quiet one. If you have that in there, the door may not be completely closed tight. And so you're likely to have a little bit of air exchange between the hallway and the bedroom. AHAM, I'm sure, had to choose some air exchange number to keep the test results in the practical world, because children don't sleep in an airtight test enclosure the way the equipment is being tested. So they had to choose something. They also had to choose
central air handler.
Yep.
If there's a central air handler, and any time that cycles, then the whole house is being turned over. So,
great point. Great point. So
yeah, it gets complicated pretty quickly.
It gets complicated pretty quickly, but it's not a direct comparison between lower door test pressures at 3 at a really big pressure differences and natural pressure differences that happen in a building with or without central air conditioning or heating system putting particles in. So it's really apples and oranges. It's two different purposes. Yeah.
Yeah. Agreed. Good question.
Yeah, great question.
Thank you. So another attendee asks, in your presentation, you mentioned that the higher the MERV rating relates to a higher level of efficiency of the filter. Could you please go into a bit more detail on MERV filters and also touch on the impacts that they have on HVAC systems?
Sure. I think that the most important thing to keep in mind is the point that we discussed during the main body of the presentation, which is that the efficiency of the filter matters almost less than the air tightness with which it's put into the system. So that's one point that I think is important to reinforce. You can have a theoretically very efficient air cleaner, but in fact is not effective because air zips around the side or the top or the bottom of the filter as it's going through the central system. So we start with that. If we could talk a little bit more about the MERV rating system, this is a system that measures the removal of particles in different size ranges, and there are several different particle size ranges that are measured in a MERV test, in a test according to to rate filters according to the MERV standard, and the small particles really are not paid much attention to until you get to MERV 13. So in MERV 6, 7, 8, 10, 11, you may have a MERV rated filter that really does a pretty good job of taking out small particles. Or you might have a MERV 11 filter that does a really crummy job of taking out small particles. You don't know because the testing range in those lower ratings really relates to overall total particle mass and not specifically the massive particles in the smaller sizes, which is the ones that we care about. So at MERV 13, now at that level, you have to report the effectiveness of removal at PM 2.5. Actually, it's a little bit different in terms of the sizes, but basically PM 2.5 range, you have to measure and report that value, and it has to be, if memory serves, something more than 50%. Terry, you might remember, and I don't, the number that you have to achieve MERV 13, but it might be 60%. I'm afraid I don't have that at my fingertips. But basically, below MERV 13, you might be getting out more, you might be getting out less, you don't know, but at MERV 13, you have a defined removal. When you go above MERV 13, 14, 15, 16, and 16 is usually described as a HEPA, a high efficiency particle arrestor, then you are getting out an increasingly large fraction of the really small particles as well as all the other particles. At the same time, you're probably making a much deeper filter to achieve that, and you may or may not be having more pressure resistance because it's a filter that is taking out more particles. That's not a direct correlation. Just because you have a higher rating does not automatically mean that you have a higher pressure drop. You might actually have a lower pressure drop, depending on how much filter fabric they decide to put in there. More filter fabric, lower pressure drop, ironically, because there's more surface area through which the air can move. Anyways, that's a lot of gibberish here. But one thing you want to keep in mind is at 13, you've got a defined amount of PM 2.5 removal, and above that, there's more, and below that, there may or may not be more. Sort of the bottom line on that.
Yeah, I think it is 50% from MERV 13 in the 0.3 to 1 micron range.
Great. Thanks, Jerry. Glad you got that one.
A follow-up question.
We're depending on my failing memory here.
Right. We should look it up.
Yeah.
Thank you. A follow-up question wonders about MERV 13 and whether or not it could stress their HVAC system, the higher the filter in there. That's
a terrific question. In other words, maybe another way to ask that is, can you do damage to your system if you put a MERV 13 in? And the answer is probably not, but it's possible. One of the other reasons that MERV 13 was chosen, in the EPA guidance is that there are MERV 13 filters available very widely that do not overstress the capacity of the system to move air. When you go above that, it gets to be a little bit dicier proposition. But you can have MERV 13 filters, even at 1 inch, that although they do add pressure drop, they add resistance to the airflow, are probably not going to add a problem. That said, if you have a system which is already short of air, because maybe the system has been squozen down, or maybe there are lots of ducts that are maybe too small, or perhaps kinked, or maybe they are flexible duct that has become kinked, or kind of looks like an octopus in the overhead, then yes, it could be a problem. But the judgment of the consulting group that helped EPA, after looking at quite a number of systems, concluded that almost certainly are not likely to have a problem at MERV 13. That said, what you'll see in the guidance is that if you don't have a MERV 13 and you want to be sure, that's certainly a very good idea to check with your HVAC professional to compare the capacity of the system in terms of airflow with the potential increase in filtration capacity. But great question, and it's the reason. One of the many reasons that a larger MERV rating was not selected for the EPA guidance.
Thanks, gentlemen. We've come to the top of the end of our presentation, so I'll just pass it back along to Lorene for closing.
Thank you, Terry and Lew. We really appreciate that you did this twice for us and all the work that you did to help on the consulting of the guidance itself. We have loads and loads of questions that were left that we couldn't get to with the time. We will hopefully be able to work with our speakers to come up with some answers for some of those and get them on the website along with the posting of both this webinar and the webinar from February 21st. We thank you all for attending, and this concludes our webinar.